So, we were discussing on gel polarization model. Now, we will be solving one problem on gel polarization model and how to calculate the gel layer thickness or pressure drop for the gel layer controlled separation process. The problem is like that: an aqueous macromolecular solution is being ultra filtered under cross flow over an asymmetric membrane of average pore size of 20 nanometer and tortuosity value is 1.7, an open area of 35% and a perm selective skin thickness of 0.45 micron. So, a plate and frame module of 7 millimeter channel depth is used. The following data are given like this for this solving this problem. A Reynolds number of the liquid which is flowing through this channel is, say, Reynolds number is 6500 and bulk solute concentration is 1.3%, solute viscosity is solution viscosity is 9.5 into 10 to the minus 3 Newton second per meter square, density is 1030 kg per meter cube and solvent viscosity is 8.8 into 10 to the power minus 4 Newton second per meter square and solute diffusivity is 3.5 into 10 to the power minus 7 centimeter square per second and pressure drop is 3 bar, temperature is 27 degree Celsius and molecular weight is 5000 and real retention is 0.99 and gel layer concentration is 12 weight percent. And diameter of the gel particle, that is average diameter dP is equal to 44 nanometer and average porosity of the gel is 0.5 and mass transfer coefficient can be calculated from this correlation. The Sherwood number is equal to 0.025 into Reynolds number to the power 0.75 and Smith number to the power 1/3 and we need to take this channel depth as the characteristic length in mass transfer correlation, means in this zone. Okay. Now, we need to calculate this gel layer thickness and pressure drop at which gel layer formation on the membrane starts. So, we need to solve this problem. So, in the beginning we will be this one mentioning which are already given in the problem. Okay. So, the tortuosity is given like say tau is given as 1.7, then thickness of the membrane is given as 0.45 into 10 to the power minus 6 meter, then epsilon is given as 0.35 of this membrane, then d is diameter of the pore is given as 20 into 10 to the power minus 9 meter, then Reynolds number is given as 6500, then Smith number actually we need to calculate, that is mu by rho into d, these are supplied, we will be calculating from there. Sherwood number we will be getting from this correlation is given like 0.025 into Reynolds number to the power 0.75 and Smith number to the power 1/3. Okay. So, that we will be getting this one, we do not know now. Then mu L is equal to say 9.5 into 10 to the power minus 3 Newton second per meter square, then density is 1030 kg per meter cube, then diffusivity value is given as 3.5 into 10 to the power minus 11 meter square per second, then real retention is given as 0.99, Cg is given as 12% and bulk concentration is given as 1.3%. So, this Cp we need to calculate from this RR value, we will be calculating Cp and then delta P that is given as say 3 bar, that is equal to 3 into 10 to the power 5 Pascal, and delta pi we need to calculate, we will be calculating this one. Then R m will be calculating, we do not know. Then R g, that also will be calculating, we do not know. This diameter of these particles which are deposited on the membrane surface, that is given as 40 into 10 to the power minus 9 meter, and we need to calculate. Then first problem is given as what will be the thickness, this L or thickness of this gel layer. Okay. So, first we will be calculating from these, actually we will be calculating this. Suppose we will be getting membrane resistance, say the formula actually will be say R m, that is we can say this membrane resistance, the formula will be also again it will be deriving this one 32 tau into L m by say epsilon into d square. So, that will be like 32 into 1.7 into 0.45 into 10 to the power minus 6 divided by 0.35 into 20 into 10 to the power minus 9 to the power 2. So, that is coming out as in the meter inverse it will be. So, that is coming out as 1.748 into 10 to the power 11 meter inverse. Okay, so, now we have this R m actually we are getting as 1.748 into 10 to the power 11 meter inverse. Okay. And then so we can calculate the Smith number, that is equal to mu by rho into d. So, mu is given as 9.5 into 10 to the power minus 3 divided by density is 1030 into d is equal to 3.5 into 10 to the power minus 11. So, that is coming out as say 2.635 into 10 to the power 5. So, now we have the Smith number we have, and we can calculate this Sherwood number, that is the correlation for Sherwood number in this high turbulence zone, say at 6500 Reynolds number, that is 0.025 into Reynolds number to the power say 6500 to the power 0.75 and Smith number 2.635 into 10 to the power 5 to the power 1/3. Okay. So, it is coming out as say 1150. This is Sherwood number is equal to we say we know K L by D. Okay. So, from here, so we can say now therefore, we can say K will be this mass transfer coefficient, we can calculate from here is equal to say 1150 into D is equal to 3.5 into 10 to the power minus 11 by L, this length is given as this 7 into 10 to the power minus 3, that is we can say meter per second. So, it is coming out as say 5.8 into 10 to the power minus 6 meter per second. Okay. So, now, so we have now this mass transfer coefficient also we have now. Now, we will be calculating, say we know this R r is equal to 1 minus C p by say here actually say C g. So, now because you see Cg and Cm both are same in this case we are assuming, then that is equal to we can say 1 minus Cp by 0.12 is equal to 0.99. From here we will be getting Cp, that is equal to say Cp is equal to 1.2 into 10 to the power minus 3 say kg per meter cube. So, now we have this Cp also we have got. Okay. Now, we will be calculating osmotic pressure gradient. Okay. So, once we know the Cp value this one, then we will be getting delta pi, that is equal to we can say this gradient in the concentration, that we can say Cg minus Cp by m into r into T. So, that is coming out as Cg is equal to 0.12 minus Cp is equal to say 1.2 into 10 to the power minus 3 into r value will be say 0.0821, T will be say 27 degree Celsius. So, it is 300 Kelvin divided by 5000 into 1000. So, it is coming out as say 0.585 atmosphere. So, it is equal to into 1.023. So, it will be like 0.593 bar is equal to say 0.593 into 10 to the power 5 Pascal. Okay. So, we have now delta pi also. Okay. So, we will be calculating now, we will be putting this one in the gel polarization model, that is we can say that we will be putting this say ln k ln say Cg minus Cp by Cb minus Cp, that is equal to delta p minus delta pi by mu into Rm plus Rg. Okay. So, here most of the terms are known except this Rg. Okay. So, now we will be putting this k is equal to say whatever we got this 5.8 into 10 to the power minus 6 ln Cg is equal to 0.12 minus 1.2 into 10 to the power minus 3 divided by Cb is equal to 0.013 minus Cp, that is same 1.2 into 10 to the power minus 3 is equal to delta p is equal to 3 into 10 to the power 5 minus 0.593 into 10 to the power 5 by mu is equal to 8.8 into 10 to the power minus 4 into Rm, we got this one as 1.748 into 10 to the power 11 plus Rg. Okay. So, from this equation we will be getting this Rg, just by calculating this we will be getting Rg is equal to 2.022 into 10 to the power 13 meter inverse. So, now we have got this Rg, we have got this delta pi. Okay. So, that we have got. Now, we will be getting this using this we can say Koźny-Karman equation. Say we know this one from there, from Koźny-Karman equation we have this Rg the function of time, that is we can say 180 into 1 minus epsilon g to the power 2 into L, that is L the thickness, by epsilon g cube, that is the for gel, and dP square, the particle size of the gel, that square. So, that will be equal to we can say we can say this 180. From there we have R g we have, and say epsilon g we have, then dp we have. From there we can say L is equal to whatever the R g value is, now we have got 2.022 into 10 to the power 13 and into epsilon g, that is we can say 0.5, that is cube, into dp is 40 into 10 to the power minus 9 square. So, L will be R g epsilon g cube dp square divided by 180 into 1 minus 0.5 square, that is. So, from there actually we will be getting L is equal to say 8.98 into 10 to the power minus 5 meter. So, we can say the thickness of gel layer actually we can say 8.98 into 10 to the power minus 5 meter. So, gel layer thickness L is equal to 8.98 into 10 to the power minus 5 meter. So, this is one answer. Now, the second question is given, problem is given like this, the pressure drop at which gel layer formation on the membrane starts. Okay, so, for that we can say means whenever we say this one, when we need this minimum delta p, where we can say this one the gel layer starts. So, that time we can say this one R g will be 0 and C g is given like 0.12. So, that is we can say this one gel layer starts. So, this is the condition we can say this one R g will be 0. So, we will be putting this one in this equation to get whatever the delta p we will be getting, because this delta pi will be, we can say this one will be same for the same system. So, we can say this using the same formula like this k into ln C g minus, again we will be putting this k into ln C g minus C p by C b minus C p will be equal to delta p minus delta pi by mu into R m plus R g. Okay. So, there actually we say R g is equal to, now it is 0. So, we can say only we need to find what will be that, in that case what will be the delta p. Okay. And say for that case we can say k will be like 5.8 into 10 to the power minus 6 ln C g, that is 0.12 minus 1.2 into 10 to the power minus 3 divided by 0.013 minus 1.2 into 10 to the power minus 3, that is equal to delta p we need to find, and delta pi is already there 0.593 into 10 to the power 5 divided by mu is equal to 8.8 into 10 to the power minus 4 into we can say mu into R m plus R g. R m is 1.748 into 10 to the power 11 into plus R g is equal to 0. So, this is the condition. From here actually we will be getting whatever delta p. So, that is we can say this one delta p will be 0.614 bar. So, that we can say this one, this is the pressure. So, we can say this one transmembrane pressure, this one at which gel layer formation on the membrane starts. So, whenever we have this 0.41614 bar pressure, that time we can say the gel layer starts forming. Okay. So, now we will be discussing about this resistance in series model. So, then the third model will be like this resistance in series model. So, this is the, say we can say for any membrane separation operation, the as the process progresses, then this suppose the solutes, some solutes will be sticked inside the membrane pores, and some layers will be formed on the membrane surface, and that is why we can say with time the throughput will go on decreasing, and that time we can say this one several resistances like say due to pore blocking or gel formation, or we can say due to osmotic pressure build up, the resistance values will go on increasing. Okay. And we can say membrane hydraulic resistance actually will remain constant, because this is the intrinsic property of the membrane, but you see other this one resistance actually will go on increasing. That is why the throughput will go on decreasing with time. So, we can say according to this model, that is resistance in series model, this flux decline is due to the combined effect of fouling of the membrane, that is may be reversible or irreversible, then concentration polarization over the membrane surface. So, these are we can say this one resistances like membrane hydraulic resistance, that is R m, that will remain constant for the entire membrane operation, because this is the property of the membrane, but reversible due to this pore blocking, say we can say this one R p b. So, that will go on increasing with time, and say gel layer type formation, say we can say due to this R g, that will also will increase, and this resistance due to osmotic pressure build up, say we can say this delta pi will go on increasing. That is why we can say the delta p minus delta pi, that effective value will go on decreasing, or resistance value we can say this one this we can say driving force will go on decreasing. Okay. So, in that case actually we will be trying to correlate all the resistances here like this in the beginning. So, whenever the pure water flux, or we can say this one time t is equal to 0. So, the that pure water flux is the multiple of membrane permeability and driving what is called pressure gradient, where this we can say this for pure water delta pi is equal to 0, that is equal to say delta p by mu into R m. But with time we can say this L p is the membrane permeability and delta p is the transmembrane pressure difference or pressure gradient. So, with time say we can say this one we will be getting the correlations like this. Now, we will be trying to correlate the all the resistance values, and we will be trying to find out the other resistance values experimentally also, and we can then tabulate the permeate flux or throughput value or output of this process with we can say the solute concentration and transmembrane pressure gradient and osmotic pressure development. Okay. So, like this we know this as from this Darcy's law, say J w is equal to, so that is we can say 1 by A dV dt, that is we can say this one flux, that is nothing but delta p by say mu into R m plus say R g plus R pore blocking. Okay. So, this R p. Okay. So, this out of these we can say this R g can be obtained from Kozny carbon equation. Kozny carbon equation we can say we can get R g value, and then like this R g, this is a function of time, that is nothing but say 180 into 1 minus epsilon g to the power 2 into L, that is the thickness, by epsilon g cube into dp square. Okay. So, from there we will be getting this R g value. Okay. So, that we can get this R m value, that this one in the previous problem we this one we wrote this one, that R m value can be obtained by this equation 32 tau into L m by mu into say L p. So, that also we can say R m also we can get this one, sorry this 32 tau into L m by epsilon into d cube. Okay. So, that where L m actually we can say this one L m is the thickness, membrane thickness, and tau is the tortuosity. This tortuosity, actually we can say the tortuosity is the ratio between this distance of pore divided by thickness of membrane. So, distance of the pore. So, if we say this the paths of the membrane is not straight, if it is not following a straight route, then distance of the pore, we can say this one will be say pore distance of this pore length divided by the thickness of the membrane. So, we can say this one, if the pore length is not straight, suppose if it is, suppose this is the membrane surface and if it is like straight, then this distance actually is same as the thickness, then we can say that will be 1, but if this distance of this like this, it is not straight, if it is a tortuous, or we can say this one, it is not, it is inclined like this, so then this distance divided by thickness. So, this thickness. So, that is why we can say in most of the cases in membrane applications, the tortuosity values are always greater than 1, and it can go up to say 3.5, means if it is very highly zigzag route like this, it may be like that way also. So, then we can say the tortuosity value will be very high. Okay. So, so now we can get this R m also will be getting from this equation, or sometimes we can get R m from this, we can say equation, that is we can say this one R m is equal to, we can say 1 by mu into L p. If we know this, we can say viscosity of this solvent as well as this permeability of the membrane, from there also we can get membrane resistance. Okay. And then we can say, then we will be getting like this for say for dead end filtration, or we can say batch cell. So, we can say this one, we can use this JW is equal to del P by say mu into say R m plus R g, that is a function of time. So, there we can say R p may be neglected. Okay. So, R p may be neglected here, and we can say this J w is equal to 1 by A dV dt, that will be is equal to say delta P by mu into R m plus R g, that will be getting from this we can say solute balance, like this we will be doing this. Suppose this for R g we can get also from the solute balance, we can do this one, we will do the mass balance on this one in the gel layer. So, we will be doing like this, suppose length of this or thickness of the gel, area of the gel area into 1 minus epsilon g, means that how much amount of this porosity is there in the gel into rho g, that will be nothing but we can see this one C b into V. So, that is we can say this how much amount of the solute concentration is there in the bulk into V. So, from there we can say this L is equal to, we will be getting like C b into V divided by A into 1 minus epsilon g into rho g. Okay. And we know this R g is equal to, we can say alpha into 1 minus epsilon g into rho g into L, that is equal to say alpha into 1 minus epsilon g into rho g, L is equal to C b into V divided by A into 1 minus epsilon g into rho g. Okay. So, that will be like this 1 minus epsilon g, then rho g will be cancelled out, then alpha into C b into V by A. So, that is R g. So, now we can write here say 1 by A is equal to say delta P divided by mu into R m plus R g is equal to we can say alpha into C b into V by A. Okay. So, from there 1 by A say we can say if we take out this, that is equal to say delta P by mu into R m, if we take out, then 1 plus alpha into C b into V by A into R m. We will be getting, that is 1 by A say dV this dt. Okay. So, from here we can say this is equal to say 1 by A delta P by mu into R m, that is nothing but we can say J 0, or in the beginning that is 1, then 1 plus alpha into C b into V by A into R m. Okay. So, now we are getting this 1 by A dV dt is equal to J 0. So, this is initial flux value J 0 plus 1 plus alpha into C b into V by A into R m. So, now we will be taking this initial condition like when t is equal to 0, we can say V will be equal to 0. Then we will be doing this integration for that this manipulating this equation, like we can say 1 plus alpha into C b into V by A into R m into dV is equal to A into integration dt into V plus alpha into C b into V square by 2 into A into R m. Okay. So, that is we can say whenever we can say V is equal to 0, that is time t is equal to 0, and when time t is equal to t, that time it will be V. Okay. So, from here we can say 1 plus alpha into C b into V by 2 A R m is equal to A into say J 0 into T by V. Okay. So, now we have this say equation like this y is equal to mx plus c, we will be putting say T by V versus say V. So, we will be getting this straight line equation, say that is we can say this one y is equal to say mx plus c. Okay. So, this that is why we are putting this T by V versus V, then we will be getting this, and then slope actually we will be getting this one is nothing but slope will be alpha into C b by 2 A into R m. Okay. So, from here actually we can say this one we will be getting this slope will be getting, from there we can get say R m is known and C b is known, area is known, say alpha will be getting. So, we can say this one using this resistance series model, we will be able to calculate all the resistance values, and then we will add all these resistance values, from there we will be able to calculate the permeate flux values. Okay. So, we will be now solving one problem. The problem is that a feed containing 27.216 kg protein, that molecular weight is 1510, in a 7560 liter solution is to be concentrated to 1512 liter by batch ultrafiltration at 25 degree Celsius using a ceramic membrane module. The initial flux value is 2.26 into 10 to the power minus 5 meter cube per meter square second at a pressure differential of 304 this bar 304 into 10 to the power, this is 3.04 bar 304 into 10 to the power 3 Pascal. Now, we need to calculate the membrane area to be provided if the job is to be done in 3 hours. The time is 3 hours. Any reduction in the driving force due to osmotic pressure is to be taken into consideration. So, we cannot neglect that osmotic pressure the gradient, or we can say this one, we cannot ignore that how much osmotic pressure is developed during this separation process in the duration of 3 hours. Complete retention of the solute can be assumed. So, we can say this one RR will be 1. So, we can Cp can be 0. Concentration, polarization and membrane fouling may be ignored. So, in that case we can say maybe concentration polarization is not taking place, or we can say this one membrane fouling is not significant. Okay. So, now we will be solving this problem. So, we will start with this we can say the solving this equation by deriving the equation for we can say the how much volume actually is varying with time, that we can do this one. So, let V be the volume of solution in the cell at any time t, and solution concentration will be, concentration is N by V, where N is mass. Okay. So, that is solution concentration is N by V. Okay. Now, we have this osmotic pressure that we cannot ignore, that is we are keeping this one as R T, this N by M into V. Okay. And we know this J W, that is equal to say minus 1 by A dV dt, or we can take 1 by A dV dt also. For that case we need to take the say boundary conditions accordingly. Okay. That is equal to, we can say this one L P into del P minus delta pi, that is R T N by M into V. Okay. So, now we can take this one, we can take out this delta pi from here, delta p from here. So, L P into delta p, this is 1 minus R T N by M V into delta p. Okay. So, now we will be doing the manipulation here. So, we can say we will be doing this V into dV just by manipulating this equation. We can say from here, from these two expressions, we can say we will be manipulating this one by V minus R T N by M into delta P, just after taking out V from here, because this V is the variable here. So, we are putting this one is equal to dV dt. So, A dt, we can say L P, then del P into A into dt. Okay. So, from there actually we are getting this, and now we are putting the boundary conditions like this. When time t is equal to 0, so will be V will be like V 0, and so that is why I say time is equal to 0, then V will be V 0. When time will be t, when time will be t, so then V 0 will be V final volume. So, this t will be like this, then final volume will be V. Okay. Now, from here we will be getting this just by putting the boundary conditions, we will be getting V 0 minus V plus n R T by m into delta p into ln V 0 minus R T n by m into delta p divided by V minus R T n by m into delta p, that is coming out as this L p, then del p into A into T. Okay. So, from there actually we know all these, we can say all these values except this L p and del p value we do not have. So, we can do one thing, we will be putting now 2.26 into 10 to the power minus 5 is equal to L p into del p into 1 minus 27216 into 0.0821 and into 298. Okay. Divided by 1510 into 7560 into 3. Okay. So, from there L p into del p, that will be obtained as 2.26 into 10 to the power minus 5 by 0.98, that is coming out at meter cube per meter square second. So, 2.305 into 10 to the power minus 5 meter cube per meter square second. So, we can say now if we put this L p into del p in this above equation, so we will be getting like this, we will be putting this in this above equation V 0 minus V. So, we will be putting this one 7560 minus 1512 plus 27216 into 0.0821 into 298 divided by 1510 into 3 ln 7560 minus 27216 into 0.0821 into 298 into 298 divided by 1510 into 3 divided by 1512 minus the same thing 27216 into 0.0821 into 298 divided by 1510, that same value this part 1510 into 3. So, from here actually we will be getting this, here you see this area is equal to L p into del p is obtained as 2.305 into 10 to the power minus 5 into area into time is equal to say 3 hours into 3600 second. So, here you see this one area will be getting as say A will be is equal to say A is equal to 25.294 meter square. So, this area actually is required for this separation. Okay. So, using this we can say resistance series model. So, we will be able to calculate all the resistances offered during the membrane separation processes. Okay. So, thank you. So, in the next class we will be discussing about this electric field enhanced membrane separation processes.